There is a moon in our solar system that is bigger than the planet Mercury. Not bigger than our moon, not bigger than Europa, bigger than a planet. It generates its own magnetic field, the only moon in our entire solar system known to do that. And beneath 150 kilometers of solid ice, scientists believe it holds more water than every ocean on Earth combined. Its name is Ganymede. It has been there the whole time, orbiting Jupiter in plain sight since long before there were humans to see it. Galileo Galilei found it through a telescope in January of 1610, the very first moon ever discovered orbiting another world. And 4 centuries later, we are still trying to understand what it really is, because everything we have learned about this moon points to the same uncomfortable conclusion. Ganymede should not exist the way it does. Its size does not match its history. Its magnetic field should have died billions of years ago. Its ocean should have frozen solid. It is hiding something. In 8 years and 7 months, the first spacecraft ever built to orbit a moon other than our own will arrive at Ganymede and finally tell us what. To understand why Ganymede is so strange, you have to start with what it should be. It orbits Jupiter at a distance of just over 1 million kilometers, closer than our moon is to Earth, but circling a planet more than 300 times more massive. It completes one orbit every 7 days. It is tidally locked, so the same face of Ganymede always points toward Jupiter, the way the same face of our moon always points toward us. It is, on paper, a moon, a rocky, icy ball of frozen material left over from the early solar system. By the simple rules of how moons work, it should be small. It should be dead. It should have cooled and stiffened and gone quiet, like our own moon did 3 billion years ago. But Ganymede did none of those things. Its diameter is 5,260 kilometers. That is wider than Mercury, the smallest planet that still counts as a planet. It is wider than the dwarf planet Pluto by a factor of more than 2. It is roughly the distance from London to New York. It is wider than Australia, coast to coast. If you placed Ganymede in front of Earth, it would cover about 40% of the face of our planet. And yet, for all that size, Ganymede is incredibly light for its bulk. Its average density is just under 2 grams per cubic centimetre, barely twice the density of water. Mercury, for comparison, has a density above 5. Earth is over 5.5. That density tells the first part of the story. Ganymede is not a rock with some ice on top. Ganymede is roughly half rock and half ice, by mass. A world built from 2 materials in almost equal measure. And that is where everything starts to get strange. Take a moment to picture the scale. If Earth were a basketball, Ganymede would be a softball, Mercury would be a baseball, Pluto would be a marble. Among the moons of the solar system, only one body is even close to Ganymede's size. Saturn's moon Titan, which is a few dozen kilometers smaller. Everything else, every other moon, every asteroid, every comet, is dramatically smaller than this. In total, there are roughly 290 known moons orbiting planets in our solar system. Ganymede is bigger than all of them. It is bigger than the smallest planet. It is bigger than the largest dwarf planet. By any sensible measure, it sits in a category of its own. So why does it not count as a planet? The answer is technical, almost legalistic. A planet, in the definition we use today, has to orbit the Sun directly. Ganymede orbits Jupiter, not the Sun. That single fact is the only thing keeping it from being classified as one of the major planetary bodies in the solar system. If Ganymede were drifting on its own, with no Jupiter to belong to, we would put it on a list right between Mercury and Mars and forget that it was ever called a moon. But it does belong to Jupiter. And that is the next part of the strangeness, because Jupiter is one of the most violent environments anywhere near Earth. Its magnetic field is 14 times stronger than our planet's, and the radiation belts that magnetic field traps are some of the most lethal regions in the solar system. Stand unshielded near Jupiter's inner belts, and you absorb a fatal dose of radiation in less than an hour. Ganymede sits inside Jupiter's magnetosphere. It rides through that radiation environment every day for over 4 billion years. That should have boiled it dry. That should have stripped away any volatiles, any atmosphere, any chance of preserving liquid water underneath. By every reasonable expectation, Ganymede should be a sterilized, irradiated rock. It is not. And in 1996, we learned why. In December of 1995, the Galileo spacecraft arrived at Jupiter. Not Galileo the astronomer, Galileo the probe, named after him. Over the next 8 years, Galileo made the most thorough survey of the Jovian system ever attempted. It flew past every major moon multiple times, and what it found at Ganymede in 1996 was something nobody had predicted. Ganymede has its own magnetic field, generated from inside the moon itself by a process that, as far as we know, is unique among all the moons in our solar system. The discovery was made by Margaret Kivelson and her team at UCLA, using Galileo's magnetometer on a single close flyby of Ganymede on June 27, 1996. The signal was unambiguous. As Galileo passed within 800 kilometers of the surface, the spacecraft's instruments measured a dipole field, a magnetic structure with a clear north and south pole, exactly like Earth's, just much smaller. Surface field strength at Ganymede's equator, 719 nanotesla. Strong enough that, if you somehow stripped away Jupiter's massive field, Ganymede would carry the only intrinsic magnetic field of any moon in the solar system. The dipole is tilted at roughly 176 degrees from the rotation axis, almost perfectly inverted, so what should be the north magnetic pole is actually buried in the southern hemisphere. The Kivelson paper appeared in Nature in late 1996, and it changed how we thought about Ganymede overnight. Because a magnetic field of that kind requires a particular thing to be happening inside the moon. It requires a dynamo. A dynamo, in the planetary sense, is what generates a magnetic field. You take a fluid conductor, usually molten iron, you stir it through convection, and the moving charges produce a magnetic field. Earth has one. The Sun has one. Jupiter has the most powerful one in the solar system. Our moon does not. Mars does not. Venus does not. Mercury surprisingly does, but a weak one. And among the dozens of moons we know of, Ganymede is the only one that has ever shown anything like this. That alone is remarkable. But the deeper problem is this. Ganymede should not have one anymore. Ganymede is 4.5 billion years old. By every model of how small bodies cool down, and Ganymede at 5,000 kilometers across is small by planetary standards, its iron core should have frozen solid long ago. The dynamo should have shut off. The magnetic field should be a fossil, lingering for a few 100 million years and then fading away. But Galileo measured it in 1996. The Juno spacecraft measured it again, much more closely, in June of 2021, during a single close pass that approached within just over 1,000 kilometers of the surface. The result was the same. Ganymede's dynamo is not a fossil. It is still running right now. Something inside that moon is still moving, still convecting, still alive. We had no real explanation for how, until a paper published earlier this year. But before we get to the new paper, there is another mystery to lay down first. Because Ganymede's magnetic field is not the only thing it is hiding. In 2015, a team led by a researcher named Joachim Saur at the University of Cologne in Germany used the Hubble Space Telescope to do something that, at the time, almost no one had attempted. He used a telescope to look inside a moon. The technique was clever. Ganymede, because it has its own magnetic field, has aurorae, exactly like the northern lights on Earth. You can see them in ultraviolet light if you have the right instruments, and Hubble does. The aurorae form along the magnetic field lines in two ovals around the magnetic poles. Now, Jupiter's magnetic field is tilted, and Jupiter rotates every 10 hours. So from Ganymede's perspective, the external magnetic environment is constantly changing, wobbling in fact on a roughly 10-hour cycle, swinging from plus 18 nanotesla in the radial direction to minus 80 and back again. That wobble should make Ganymede's aurorae rock back and forth like a swing, and by how much they rock you can tell what is inside the moon. Because if Ganymede has a deep, conductive, salty ocean beneath its ice, that ocean acts like a Faraday shield. It generates its own induced magnetic field that opposes Jupiter's wobble. The aurorae get damped. They do not swing as far. Saur did the calculation. If Ganymede had no internal ocean, the aurorae should rock back and forth by about 5.8 degrees on average, give or take 1.3 degrees of measurement uncertainty. If Ganymede did have a salty ocean, the aurorae would only rock by about 2.2 degrees. He took the observations, he measured the rocking. The answer came in at 2.0 degrees, plus or minus 1.3. It is hard to overstate what that result means. Saur did not photograph the ocean. He did not drill into it. He did not even fly past it. He used a telescope more than 500 million kilometers away to detect a 4-degree wobble in invisible ultraviolet light, and that 4-degree damping is, to this day, the entire scientific evidence base for the largest ocean of liquid water in our solar system. In his own words, recounted in the NASA press release at the time, "Is there a way you could use a telescope to look inside a planetary body?" Then I thought, the aurorae. What the data tells us about that ocean is this. It begins somewhere between 150 and 250 kilometers beneath the surface. It is at least 100 kilometers thick. It is saltier than Earth's seawater in some models, fresher in others. The minimum conductivity Saur's technique can rule out is just under 1/10 of a Siemens per meter, barely 2% as conductive as Earth's oceans. The total volume is enormous. NASA's official summary, which has held up since, more water than all of Earth's surface water combined. You should sit with that for a moment. Every drop of water that has ever fallen as rain on Earth, every river, every lake, every sea, every ocean. Lake Baikal, the Pacific, the Atlantic, the Indian Ocean, the polar caps. Take all of it, pour it together, and you would not fill Ganymede's hidden ocean. There would still be more, kilometers deep on a moon you cannot see with the naked eye, orbiting a planet most people could not point out in the night sky. It has been there for the entire history of life on Earth, and we found it by watching auroras wobble. The Saur paper made the strongest case for the ocean. But it did not stand alone. In 2023, a team led by Federico Tosi used a different instrument, the GIRAM spectrometer on board the Juno spacecraft, to look at Ganymede's surface in infrared light. Where Hubble could only watch the auroras, Juno could fly close and look at what was sitting on the ice itself. What GIRAM found was unexpected. The surface of Ganymede in certain regions contains hydrated sodium chloride, table salt. It contains ammonium chloride. It contains sodium bicarbonate, baking soda, and there are spectral features consistent with aliphatic aldehydes, which is a class of simple organic compounds. These are best fit interpretations, not direct samples. GIRAM cannot scoop the surface. It can only match the infrared fingerprints of what it sees against laboratory data. But the matches are compelling, and the pattern is even more striking than the chemistry alone. The concentrations of these compounds are highest in Ganymede's magnetically shielded mid-latitudes, the regions of the Moon best protected from Jupiter's radiation bombardment. The leading interpretation is straightforward, if extraordinary. These salts and organic precursors did not come from outside, they came from below. Brines from the deep ocean have somehow worked their way up through the ice, reached the surface, and frozen there. The protected mid-latitudes preserve them. The unprotected polar and equatorial regions get them stripped away by charged particles. If that interpretation is correct, Ganymede's ocean is not a sealed black box. It is in chemical contact, however slowly, with the surface above it, and what reaches the surface is exactly the kind of chemistry, salt, ammonia, simple organics, that astrobiologists look for when they ask whether a place could host life. This is not a discovery of life on Ganymede. It is a discovery of the ingredients that life needs, in the place we already had reason to believe was the most likely candidate, and the question of whether anything more than ingredients is actually down there, whether the ocean itself contains anything alive, is something only one mission, currently in flight, can begin to answer. The European Space Agency calls it JUICE, the Jupiter Icy Moons Explorer. It launched from French Guiana on the 14th of April 2023 on an Ariane 5 rocket. It is, by mass, the largest interplanetary mission ever built by the European Space Agency. Its solar panels, necessary because Jupiter receives only about 4% of the sunlight Earth does, cover roughly 85 square meters, the largest ever flown on any spacecraft headed away from the inner solar system. Dry mass, 2,400 kilograms. Fully fueled at launch, 6,000 kilograms. Mission cost, roughly €1.5 billion. JUICE is currently in space. Right now, as you're watching this, it has already completed 3 gravity assist flybys, first past Earth and our Moon in August of 2024, then past Venus in August of 2025. It is in its 3rd long cruise phase as I record this, drifting on a calculated arc that will bring it back past Earth in the autumn of 2026 for its 2nd Earth flyby, then again in early 2029 for its 3rd. The plan from there is precise. Continue cruising until 2031, arrive at Jupiter in late July of that year. Spend the next 3.5 years touring the Jovian system, completing 35 flybys, of Jupiter's major moons. And then, in December of 2034, JUICE will do something no spacecraft has ever done. It will break into orbit around Ganymede. Take a moment with that sentence. Every spacecraft that has ever orbited a moon has orbited our moon, the one we see from Earth every night. Apollo, Lunar Orbiter, Chang'e, Chandrayaan, dozens of others. Every single one of them has orbited the same body. JUICE will be the first spacecraft to enter bound orbit around any other moon in any solar system in history. The first phase will be a 12-hour polar orbit. Over the next 100 days, the periapsis, the lowest point in each orbit, will be progressively lowered until JUICE is circling at roughly 500 kilometers altitude. 6 months of intensive science from that orbit. Then a final low orbit at around 200 kilometers, until the radiation budget is finally exhausted and the mission ends. JUICE will then impact Ganymede's surface, intentionally, somewhere in late 2035, leaving the first human-made object permanently embedded in the moon. Among the 10 instruments on board, 2 matter most for the questions we have been asking. The first is RIME, the radar for icy moon exploration. It is a ground-penetrating radar built to send pulses through up to 9 kilometers of ice and listen for what bounces back. RIME will be the closest thing we have ever had to looking directly at the structure of the ice shell sitting above Ganymede's ocean. The second is JMAG, the magnetometer. It is an exquisite instrument, accurate to 1/5 of a nanotesla at 1 measurement per second, and it is going to attempt something that has never been done at any moon in our solar system. It is going to try to measure the speed and direction of currents inside an alien ocean. In 2025, a paper appeared in Geophysical Research Letters. Lead author, a researcher named Cabanes, working with collaborators in fluid dynamics and planetary physics. The title was technical, Motional Induction in Ganymede's Ocean. The implications were not. Cabanes and his team asked a question nobody had answered cleanly before. If Ganymede's ocean is liquid and salty and conductive, then the ocean is going to circulate. There will be currents, the way there are currents in Earth's oceans. Those currents will flow through Ganymede's magnetic field. And when a conductive fluid flows through a magnetic field, it generates an electrical effect, a magnetic signature that, in principle, can be measured from outside. The team modelled it. They found that under the most favourable conditions, a deep ocean, around 500 kilometers thick with strong east-west jets and high conductivity, the surface magnetic perturbations could reach about 9 nanotesla. 9 nanotesla is small. To put it in scale, Ganymede's own intrinsic dipole at the surface is over 700 nanotesla. The background variations driven by Jupiter's wobble are tens of nanotesla. 9 nanotesla is signal hiding under noise, but JMAG was built precisely for this kind of work. Its scalar sensor measures to 1/5 of a nanotesla. The signal-to-noise ratio on a sustained 9 nanotesla feature would be tens of times above the instrument's noise floor. The challenge would not be detection. The challenge would be separation, pulling that ocean current signal out from the much larger background fields it sits inside. And here is the elegant part of the Cabanes paper. It explains why Ganymede is uniquely well suited for this measurement, in a way Europa is not. Europa, you may know, is the other Jovian moon with a strong case for a subsurface ocean. But Europa has no intrinsic magnetic field of its own. At Europa, there is only Jupiter's external field to work with, and that field is weaker, varies in only one orientation, and gives less leverage for the ocean to generate detectable currents. Ganymede is different. Ganymede's own dipole reaches deep into the ocean. The internal currents flowing through that intrinsic field experience much stronger forces, generate stronger toroidal magnetic structures, and produce a detectable poloidal signature at the surface that Europa simply cannot match. The takeaway is this: if Ganymede's ocean is deep, conductive, and circulating, and there is real reason to believe it is, then JUICE will be the first spacecraft in history to measure the speed and direction of currents in an extraterrestrial ocean. It is not guaranteed. Weaker ocean configurations would produce signals close to or below 1 nanotesla, hard to confirm. The full measurement requires months of sustained observation from low orbit. The science depends on whether the ocean is as active as the models hope. But the instrument is there. The mission is in flight. The answer is coming. There is one more piece, and it is the strangest piece of all, because there is still a problem we have not solved. We have an ocean. We have a magnetic field. We have surface chemistry consistent with brines from below. We have a mission that will plausibly measure currents in that ocean inside the next decade. But we still cannot explain how the magnetic field is even possible. Ganymede is 4.5 billion years old. Its iron core should have frozen long ago. The dynamo should be dead. Earlier this year, a team led by Carl Trin and colleagues, working with planetary scientists at NASA's Jet Propulsion Laboratory, published a paper in Science Advances. The title was simple: Powering Ganymede's Dynamo with Protracted Core Formation. The argument is extraordinary. Trin's team built a thermal evolution model of Ganymede's interior, what its temperature, pressure, and composition looked like over the last 4.5 billion years, and they found that the standard picture, where Ganymede differentiated cleanly and quickly into a rocky mantle and a metallic core, does not work. Under that picture, the core freezes and the dynamo dies. End of story. But there is another picture, one where Ganymede never fully differentiated in the first place. One where, 4.5 billion years after it formed, parts of Ganymede's interior are still slowly separating, where iron is still draining out of the silicate mantle and joining the growing protocore at the center. If that is true, Ganymede's metallic core is still being assembled today, right now. As you're watching this, every iron atom that finds its way down to the core releases gravitational energy as it falls. That energy heats the surrounding material. That heat drives convection. That convection drives a dynamo. That dynamo produces the magnetic field that JUICE will measure when it arrives in 2034. If Trin's team is right, Ganymede may be the only world in our solar system where the basic process of core formation, the same process that built Earth's core 4.5 billion years ago and finished by maybe 2 billion years ago, is still happening in slow motion today. We are not looking at a finished moon. We are looking at a moon that, in some deep and structural way, is still being built. Europa gets the attention. There is a reason for that. Europa's ice shell is thin, perhaps only a few kilometers in places. Its ocean is right there, almost within reach. NASA's Europa Clipper is on its way to Europa right now, due to arrive in 2030, carrying 9 carefully chosen instruments. The story of Europa is the story of a place where, if life exists, it might be relatively close to the surface, relatively easy to find. But the story of Ganymede is bigger, in every literal and metaphorical sense. Ganymede is the larger world. Its ocean is the larger ocean, by raw volume of liquid water, the biggest known body of water of any kind in our solar system. Its protective shell of ice, 150 kilometers of it, is the thicker shield. Its magnetic field is the only one of its kind anywhere among the moons we know, and the engine driving that magnetic field, if the 2025 work holds up, may be a process of planetary construction still actively underway. Europa is exciting because it might be accessible. Ganymede is profound because of what it is. Arthur C. Clarke understood this. In his 1982 novel 2010, Odyssey 2, the sequel to 2001, the great black monolith near Jupiter delivers a famous warning. All these worlds are yours except Europa. Attempt no landings there. Europa was sealed off by mystery, reserved for something else. The Jovian system was left open to humanity, and in the later novels of Clarke's Space Odyssey sequence, Ganymede, not Europa, is the moon where the first colonies are eventually built. In our reality, this remains true. Ganymede's surface receives roughly 67 times less radiation than Europa's. If humans ever do walk on a moon of Jupiter, Ganymede is where they will walk first. So here is what we now know, and what we're about to learn. We know that Ganymede is bigger than Mercury. We know it carries the only known intrinsic magnetic field of any moon. We know there is, beneath 150 kilometers of ice, an ocean of liquid water holding more volume than every ocean on Earth combined. We know that brines from that ocean reach the surface and freeze there, carrying salts and possibly the basic ingredients of organic chemistry. And we know that the dynamo powering all of this should, by every conservative model, have died billions of years ago, but did not, possibly because the moon's interior is still in the process of forming itself. These are facts, or as close to facts as we have for any world we have never landed on. What we're about to learn is hard to summarize. JUICE will arrive at Jupiter in 2031. 3 years later, in December of 2034, it will become the first spacecraft in human history to orbit a moon other than our own. For the better part of a year after that, it will look directly at Ganymede with 10 instruments: radar that can see kilometers deep into the ice, a magnetometer that can measure the wash of unseen currents, spectrometers that can read the chemistry of the surface in fine detail. Some of what JUICE finds will confirm what we already suspect. Some of it will probably overturn it. Almost all of it will be data that no human being has ever had access to before. There is a reasonable chance that, in your lifetime, you will see the first measurement of an ocean current on another world. There is a reasonable chance that, before the decade after that is out, we will know whether the chemistry inside Ganymede's hidden ocean is the kind that biology anywhere would recognize. And on a very long enough timeline, generations after this, there is a chance that one of the first places a human being stands, on a world that is not the Earth or its moon or Mars, is on the cratered grey-brown ice of a moon larger than the planet Mercury, with a quiet ocean beneath their boots, and Jupiter hanging in the sky overhead like a permanent dawn. Ganymede has been hiding something for 4.5 billion years. In December of 2034, it stops hiding. We have been looking at that moon for 400 years. Galileo Galilei saw it as a single point of light through a hand-built telescope in the winter of 1610, and did not know, could not have known, what he was looking at. In December of 2034, a spacecraft built by his great many times removed scientific descendants will arrive in orbit around the same point of light and finally tell us. If you want to keep tracking the spacecraft and the discoveries actually reshaping how we understand our solar system, subscribe because there is a lot more out there.